Hello guys, so this is second lecture of acidic strength and we were discussing about how to identify the acidic strength of the molecules by using all the electronic effects what we have learned till date and how to implement them, how to basically figure out which molecule is more acidic and which one is less. So I had shown you many examples in the last class and today we'll be talking about few important concepts where we will be using them for carboxylic acid, amines and all that for finding out their acidic strength. Or you can say multiple compounds having benzene and the functional groups over them, how to identify which one is more acidic and which one is less. So for that, few important concept needs to be covered. So let's start aromatic acids. So in case of aromatic acids, the most common acid is carboxylic acid, or you can say the most common and most known, or you can say most used acid in terms of aromatic acid is benzoic acid. Benzoic acid can be substituted also and can be a non-substituted benzoic acid also. If it is substituted, whether it will the substitution will increase the acidic strength or will decrease the acidic strength, that we have to understand. And what concept we will apply, what are different concepts we have to keep in mind before deciding on the acidic strength part. Okay, so aromatic acids can have of multiple different types. We have a normal benzoic acid. This is my normal benzoic acid, and we can have the benzoic acid with electron withdrawing group, which can be an ortho, para and meta position. So it can be placed in any position, ortho, para and meta, right? And then we can have a benzoic acid which is substituted with electron releasing group. Electron releasing group is the one which will give the electron density in the benzene chain, and electron withdrawing group is the group which will pull out the electron density from the benzene chain or from the benzoic acid. Now understand one thing, if it is electron withdrawing group which is present on the benzene, then it always pulls the electron density from that benzoic acid. So if you are comparing a normal benzoic acid, this is your normal benzoic acid, and then you have a benzoic acid with electron withdrawing group present like NO2 on this position, or NO2 on meta position, or NO2 on the para position. In either case, this NO2 is going to be electron withdrawing group. In the case of ortho and in the case of para, it is the resonance based group. Okay, basically resonance impact is on ortho and para. When NO2 is on the meta position, then it is electron withdrawing due to its inductive effect, because on the meta positions resonance don't work, or you can say resonance has no impact on the meta positions. Right? So with respect to NO2, your COH is on the meta position, so we will not consider the NO2's mesomeric effect, but we'll be talking about inductive effect, and inductive effect also is electron withdrawing over here. So in either case, no matter you talk about the ortho substituted or meta substituted or para substituted benzoic acid, which is substituted by electron withdrawing group. Electron withdrawing group will be pulling the electron density from the benzoic acid. And what will happen? Thus, the acidity in benzoic acid is due to this OH bond. Okay, now this oxygen is electronegative, hydrogen is electropositive. Oxygen always wants to pull the electron density towards itself, and that is why it is always partial negative, and hydrogen is always partial positive. When this H goes out, that shows the acidic strength. The ease of releasing H plus ion by any molecule is the acidic strength. So how strongly oxygen is able to pull the electron density, that will decide how strong your carboxylic acid is. So if there is an electron withdrawing group present on this benzene anywhere, then that electron withdrawing effect will be visible on this COOH also, and that will be visible on this oxygen also. So basically, oxygen is anyways electronegative, wants to pull the electron density from hydrogen, and there is somebody else also which is pulling electron density from oxygen. So I had explained you this concept in the live class also, that oxygen was anyways trying to pull the electron density from hydrogen. Now there is a better group there, or now there is another bully there which is trying to pull the electron density from oxygen. So oxygen was desperate to pull electron density. Now it has become furthermore desperate to pull electron density from hydrogen, and will kick out the hydrogen much more easily. So electron withdrawing groups make the acids more stronger, and electron donating groups decrease the acidic strength. So if I have a benzoic acid with electron withdrawing group on either position, ortho, para or meta, then it is going to be very acidic. because that electron withdrawing group will pull the electron density from oxygen also, and oxygen will become more desperate to break its bond with hydrogen, and the ease of releasing H plus will be faster, right? Faster than benzoic acid. Okay, and when it is electron releasing group, then oxygen has this desperation of taking electron density from hydrogen. But if electron releasing group is present in the benzoic acid, it will basically give density to oxygen, so that desperation will decrease to break the bond with hydrogen. If that desperation will decrease, that means bond will not break so easily, or in that faster mode, or it will not, the breakage of bond between oxygen and hydrogen will not be fast as it will be in the case of benzoic acid, or it will be in the case of substituted benzoic acid, where substitution is with electron withdrawing group. So your electron donating group basically decreases the acidic strength by partially fulfilling the need of electron, which is there for oxygen wants electron, and that need will be fulfilled by electron donating group, and hence oxygen will not break bond with hydrogen so easily. Okay, so most acidic aromatic acid will be the one which is substituted with electron withdrawing group, then your normal benzoic acid, and then one with the electron releasing group. That's how the generic order is gonna be. Now, if you have to basically decide in similar type of compounds, like what I mean by similar type of compounds, if I have a compound which I had shown you just now, if I have COOH with, let's suppose, any functional group on ortho position, functional group on meta position, and functional group on the para position, and assume this group is same, no matter it can be electron withdrawing group or it can be electron releasing group, how will you arrange these compounds in their acidic strength order? What you will use to decide the acidic strength of these compounds, considering electron releasing effect, considering electron withdrawing effect, or considering all other electronic effects which we have spoken about, and is there any other factor which can affect the acidity of this benzoic acid, the substituted benzoic acid, that we have to learn. So we are going to learn a topic, or we are going to learn a concept which is called this ortho effect, which is very important to understand how the acidic strength of benzoic acid gets affected by the presence of the functional group, electron withdrawing, electron releasing, or whatsoever. And before that, before we understand the ortho effect, I will explain you what is steric inhibition of resonance, which is a broader concept, not only specific to benzoic acid, but any functional group which is sterically hindered. Okay, so let's understand the steric inhibition of resonance, and then I'll come to the ortho effect. Now let's talk about steric inhibition of resonance. Let me just write it over here. So it is this effect is also called as SIR. Okay, in short, this is called as SIR. First of all, understand the terminology, understand the meaning of each and every term which I have used over here. Steric inhibition. Steric means traffic. Traffic is called as steric. Steric hindrance means more and more bulkier groups are present. That bulky group can be alkyl group, or bulky group means anything which is bigger in size, basically create the hindrance in any particular reaction to happen, or any particular procedure to happen, or any particular mechanism to happen. So if more and more R groups are present on anything, or more and more alkyl groups are present at one position, that position become too crowded. Any crowded place is called as steric inhibited place, or steric inhibition, or steric hindrance. Steric hindrance is nothing else but overcrowding at a particular position. Okay, now what do we mean by steric inhibition of resonance? Due to overcrowding at particular position, when resonance stops, this is called as steric inhibition of resonance. Now, where does it happen and how does it happen? Let's understand. So I have this as a benzene, this benzene chain. Okay, now on this benzene chain, let me just write it this way. I have this benzene chain, and I have a functional group over here which is a big functional group, which is a bulky functional group. Like let's suppose I have taken CH3 and CH3. So this is pretty big functional group. So it is tertiary amine, and it is quite bulky because it has two R groups present. So now what happens over here is, now if you're talking about this particular functional group over here, it's pretty crowded. Okay, now along with this functional group, if I attach one more functional group at the neighboring position, for example, if I, let's suppose, put CH3 over here, Okay, so I have NCH3, CH3, and I have one CH3 over here. This is electron releasing group. Okay, or I can have an electron withdrawing group also. It really doesn't matter, by the way. Okay, I can have N with CH3. I mean, it's not the only example, but I have taken this just to explain you. Let's say I have COH over here, or what else can I take? I can have NO2 over here. So any such functional group is present in the neighborhood, that is on the ortho position. Okay, so what will happen is, so I have taken three cases. One is I have benzene with N CH3 CH3, so there is no other substitution at ortho position. Then I have taken one in which I have an electron leasing group present on the ortho position, and I have an electron donating group electron withdrawing group present on the ortho position. Now what will happen is, this nitrogen has no, this is a big bulky group, but it has no crowding on the neighboring sites, which can stop its resonance. It is a bulky group, but it can do the resonance by giving its pair of electron to the benzene chain, and then this is an electron, this is a plus M group basically. So this will gain a plus charge on it, and the electron will rotate in the benzene, and the negative charge density will get distributed in the whole benzene. This is normal behavior. Now let's suppose if CH3 or NO2 is present in the surroundings, or any other functional group is present in the surroundings, what will happen is, these are too close to each other. So this group and this group is too close to each other, and as we can clearly see that this group is quite a bulky group. So the presence of CH3 will affect this group. How will it affect this group? See, for resonance we require our lone pair to be in the parallel p orbital, so that it can resonate, it can share its electrons to the neighboring carbon, and that those electrons can go move around the whole benzene chain. But because so that means this NCH3CH3 and this CH3 will be in the same plane. But if these two groups, this group and this group, if both groups are gonna be in the same plane, then what's gonna happen is, there is gonna be a huge repulsion. To avoid that repulsion, what my nitrogen will do, my nitrogen will try to avoid repulsion by rotating itself through this single bond, and it will rotate itself in such a way that the pair of electron which was in the plane, in the parallel plane to the carbon's p orbitals, it will go out of plane. So it will rotate itself in such a way that your nitrogen goes out of the plane. When nitrogen will go out of the plane, the pair of electrons p orbital will also go out of the plane. If p orbitals electrons will go out of the plane, or the p orbital will go out of the plane, then the resonance will not happen. Then this pair of electron cannot be shared in the benzene. So basically, this nitrogen, what it looks like right now is, it is in plane with benzene, and this nitrogen and this CH3 are also in plane, are in the same plane. This nitrogen will go out of the plane by rotation, and now it will be, if it is straight now, it will rotate in such a way that it will be pointing towards the viewer. So it will basically, through rotation, it will change its plane, and this will go out of the plane. Through rotation, it will go out of the plane, and it will go out of the plane so that it can avoid the repulsion which is happening with CH3. As soon as it will go out of the plane, the repulsions will be minimized, but at the same time, the p orbital which was in parallel to the other p orbitals with what it can do the resonance, it will not be parallel now, and the resonance will stop. This is called as steric inhibition of resonance. So basically, this lone pair is in conjugation with the pi bonds over here, but still it will not be able to participate in the resonance, because the electrons, or lone pair of electrons, are in different plane, or p orbital is not parallel to the carbon's p orbital. You got the point? So what I'm trying to tell you, to avoid the repulsion, my nitrogen will go out of the plane, and that will cause the p orbital which was participating in the resonance to go out of the plane. If that will go out of the plane, the electron, the pair of electron which was there in the nitrogen, which was participating in the resonance earlier, will not be able to resonate. And the resonance will stop. So resonance will happen in the benzene. So benzene's resonance will not stop, but nitrogen will not be able to donate its pair to the benzene chain. So resonance will not be there. And the pair of electron, which was a delocalized pair of electron earlier, will become a localized pair of electron. It will be a local pair. Of electron. Now, this is not very specific to CH3. The same thing will happen when the CH3 is around, and the same thing will happen when NO2 is around. So it won't matter whether electron withdrawing group is present or electron releasing group is present. If any group is present in the ortho position, that will cause the nitrogen to go out of the plane and the p orbital to go out of the plane, and eventually the resonance will stop. So electron releasing and electron donating effect will have no impact in general. Basically, the electron releasing, irrespective of electron donating or electron releasing effect, the resonance will stop. Only inductive effect will work, but resonance will not work. So that is what exactly is steric inhibition of resonance. Now, how do we implement this concept where all it is used? Now let me explain you. Now, as I said that I have compared two structures. This is my structure which has no where the no group is present on the ortho position, and this is my structure where I have I'm just writing it this way. I have NO2 present over here, or CH3 is present over here, whatsoever. So this will face the repulsion, and this NHN will go out of the plane, and this pair of electron which was earlier participating in the resonance, due to the presence of NO2, this will go out of the plane, and this will be localized lone pair. Whereas this one can still participate in the resonance, and this will be delocalized lone pair. When it is delocalized lone pair, it is not completely with nitrogen, so basic strength, this will affect the basic strength of the molecule. So what does basic strength means? Basic strength means more the electron density will be present on nitrogen, more basic it will be. Okay, if I talk about this compound, the first compound, here the pair of electron is not localized, it is not staying with nitrogen for a longer time. Instead, this electron density is getting distributed in the whole ring due to the resonance. And out of, let's suppose this has 5 resonating structures. Out of 5, only 2 resonating structures have basically the electron pair with nitrogen, and rest of the 3 structures have electrons in the benzene chain, and nitrogen is carrying positive charge. So basically, if you look at the molecule, the lone pair which nitrogen has is not its own lone pair, it is getting distributed throughout in the ring, so electron density is lesser. Whereas if you talk about this case, the second case, in second case, because the resonance has stopped, this lone pair will not go anywhere, it will remain with the nitrogen. This is the localized pair of electron, and hence I can say the electron density is more on this nitrogen as compared to this nitrogen. We can say electron density is more on nitrogen of compound 2 as compared to nitrogen of compound 1. Hence, if somebody will ask me which one is more basic, second compound is more basic than the first compound. So this is my steric inhibition of resonance. Okay, this is not very specific to nitrogen or nitrogen with 2 CH3s. It is about any bulky group which is present on benzene, and if it has some functional groups or any group present on the ortho position. Where all the steric inhibition of resonance does not work, let me just tell you. So here is an important note. Presence of O minus, OH minus, NH2 or CN does not causes steric inhibition of resonance. Basically, if these groups are present on the ortho position with some other group, they will not cause steric inhibition of resonance. Or if these groups are present, let's suppose, let me give you an example. What I'm trying to tell you is, if I have benzene with OH and then CH3 on the ortho position, no SIR here. Okay, similarly, if I would have, let's suppose, nitrogen with CH3 and CH3 here, and with OH here, or CN here, or O minus here, or NH2 here, this wouldn't have caused the steric inhibition of resonance. Why? Because these groups are extremely small and they do not cause the repulsion of any kind, and hence the rotation of molecule doesn't happen, and hence the molecule doesn't go out of the plane. So neither your O minus, OH, NH2 and CN experience any kind of steric inhibition of resonance, nor they exert any kind of SIR. This is a very, very important point. Okay, now let's talk about the ortho effect, which is very important to understand the acidic strength of the substituted benzoic acids. So that is based on this SIR, hence we have covered this SIR first, and now we will understand the specific case of benzoic acid. So what is ortho effect? Ortho effect is very specific to benzoic acid. We use this term for benzoic acid only. When any group is present at ortho position of benzoic acid, then irrespective of its nature, no matter it is electron withdrawing or electron releasing, it increases the acidic strength. Basically, your molecule will be more stronger acid as compared to a normal benzoic acid. So what I mean to say, if I have this compound, benzoic acid, with a group present on the ortho position, no matter this group is electron releasing or this group is electron withdrawing, this will be more acidic than the benzoic acid. If you would have noticed, I have also mentioned this thing here. So I have written electron releasing group on meta and para position only. I have not mentioned ortho position, because if an electron releasing group present on the ortho position, then its acidic strength is gonna be more than your normal benzoic acid. So any benzoic acid with electron releasing group present on the meta and para position is the one which is lesser acidic. But if it is on the ortho position, no matter it is electron withdrawing group or electron releasing group, it will be more acidic than the normal benzoic acid. How? Why? Let's understand. So here we have two reasons for ortho effect. One is steric inhibition of resonance, which we have learned just now, and there are some electronic factors also. But before we go in depth of this, one thing which you have to understand is, as I mentioned, ortho effect is irrespective of you have electron releasing group present on the ortho position or electron withdrawing group present on the ortho position. These groups, if they are present on the ortho position with respect to COH, they are going to increase the acidic strength of benzoic acid, of substituted benzoic acid. But there are some exceptions. If OCH3 is present on the ortho position or NH2 is present on the ortho position, they do not cause the ortho effect. Basically, the presence of these groups will not increase the acidic strength of substituted benzoic acid. The acidic strength of these benzoic acids will be lesser than the normal benzoic acid, but in case of all other functional groups, this will work. Okay, so let's understand ortho effect, which happens due to steric inhibition of resonance. Please understand it slowly. If you are not able to understand, go back to SIR, understand the steric inhibition of resonance first, and then come back to the ortho effect. Ortho effect is the result of steric inhibition of resonance. So once you understand SIR, you will be able to understand the ortho effect also. Now, what is ortho effect? In ortho effect, you see I have a benzoic acid ka COH group present here, which is the big bulky group. Okay, if you talk about the carboxylic acid, the oxygen has the tendency of pulling the electron density towards itself. This oxygen is pulling the electron density towards itself, and this oxygen which is attached with the carbon through the single bond, that will give the electron density, and eventually it becomes like this. So it becomes O minus and it becomes O plus. Till now I am not talking about the resonance in the benzene chain. I have just spoken about the electron shift in only COH group. So benzene group has not been touched yet. Benzene has not been touched yet. So basically, the resonance is possible within COOH group also, and the resonance is possible with the benzene chain also. When you talk about COOH, its own resonance, these pair of electrons are in conjugation with this pi bond. So irrespective of what is present over here, the COH itself can perform the resonance by moving this electron density here and pushing this electron density here. Okay, so if this resonance will happen in only COH group, this is how the electron transfer will be. So one oxygen will become negative, and oxygen which is bonded with hydrogen will carry a positive charge, right? Positive charge on oxygen is definitely not stable. But is it getting stabilized by some way? Let's see. So here, as soon as this positive charge will be created over here, the electron supply can happen from the benzene chain. Now this pi bond can split and the electron density can be shifted to this carbon. Just look at it over here. So I have this CO minus double bond O plus H. Now this double bond is in conjugation with this double bond, and this can start doing resonance. When it will do resonance, what will happen? This pi bond will break, will give the electron density here, and this pi bond will break and will shift like this. So this will be how it will be. It will be like this. So here you have negative charge on this oxygen, then this will become okay, let me correct it. So here this pi bond has got shifted, so there is gonna be positive charge over here. This carbon and this oxygen would have got the electron density back. So the positive charge what it had, it got it back from the carbon double bond oxygen, and this carbon got the electron density from the benzene chain. So here is a pi bond over here. So this has become like this, right? So basically now this positive charge will get dispersed in the whole benzene chain. So first of all, your oxygen got the electron density back from the benzene, so there is a back supply of electrons from the ring. So what we expected was that oxygen with a positive charge will be highly unstable and it will kick out hydrogen faster, but it got the back supply from the benzene. It got the electrons from the benzene due to the resonance. So basically it got the electron density back, and it will not be very desperate to remove the hydrogen from itself. So basically why it is happening? Because the oxygen got the back supply from benzene, and the positive charge which this oxygen was carrying, because of which it would have got the desperation, that has got reduced due to the back supply of electron from benzene through the resonance. This is the case when you are talking about the normal benzoic acid. Okay, now let's suppose if there is a group present on the ortho position. If there's a group present on the ortho position, what exactly will happen? Let me just show you. So if there is a group present on the benzoic acid, okay, what will happen is, this is my benzene chain, okay, and this is my carbon, and there is now first of all the resonance will happen within COH. So this will pull the electron density, and this lone pair will go here like this. So this oxygen will be negative, this oxygen will be positive, and there will be a pi bond over here and a hydrogen. And if there is a functional group present over here, what exactly is going to happen? So there will be a functional group or any group present over here that will cause the repulsion to the COH, because COH is a bulky group. To avoid that repulsion, the COH will rotate itself in such a way that the p orbital of oxygen and the carbon which was participating in the resonance will go out of the plane. So the carbon's p orbital, this p orbital which was in conjugation with this p orbital, this p orbital, this p orbital, this p orbital, so basically this p orbital was in parallel to the p orbital of the carbons of benzene. When this carbon of COH will rotate itself, that p orbital will also go out of the plane. If that p orbital will go out of the plane, it will not be able to participate in the resonance. Oxygen's p orbital will go out of the plane, the carbon's p orbital will go out of the plane, and hence the resonance will stop. So resonance will stop. So this COOH will be doing resonance within itself but not with benzene. Hence the back supply of electron which this oxygen was getting, there was electron density it was getting due to the resonance which was happening in the benzene. So benzene was giving the electron density on the carbon. So if you remember, I had shown you in the last slide that what had happened when it was only COH, what was happening basically, this oxygen was getting electron density from this carbon, and this carbon was getting electron density from benzene. So the electron was supplied by this benzene, right? But now this is not possible. Benzene will not be able to give its electrons to the carbon, and carbon hence will not be able to give electron to the oxygen. So oxygen will be positively charged here now. It cannot participate. This carbon double bond oxygen is not participating in resonance with benzene. Hence this oxygen will remain with the positive charge. Oxygen with the positive charge is highly electronegative and will be highly desperate to break the bond with hydrogen. So this will quickly kick out this hydrogen out of it to maintain its electron density, and this H plus will be out. So if you compare a benzene chain or benzoic acid with the functional group present along with COOH, that functional group will make the COH group out of resonance, and hence the oxygen which is carrying positive charge on it, which is associated with hydrogen, will not get any electron supply, and hence the positive charge will remain with that oxygen. If it will remain with the oxygen will be desperate to kick out H as H plus to gain back the electron density, and hence it will be more acidic than your normal benzoic acid. Why? Because in case of normal benzoic acid, you are getting supply from the benzene. You are getting supply from benzene, right? So that is the reason why in the ortho effect, it really doesn't matter what group is present over here. It can be electron releasing group, it can be electron withdrawing group. In either the case, the repulsion will happen, and repulsion will stop the COH group to resonate with benzene, and hence the back supply of electron from benzene to COH group will stop, and oxygen will carry a positive charge. If it will carry the positive charge, it will kick out the hydrogen faster, and H plus will be out faster, and hence that substituted benzoic acid will be much more acidic than the normal benzoic acid. So this is about ortho effect, and this is what I have explained you in this slide also. This is your normal benzoic acid. It is getting back supply of electron for this oxygen from the benzene ring, but this is a ortho substituted benzoic acid, where there is a group present over here. That group can be electron withdrawing, can be electron releasing, but this is stopping the resonance, no resonance from benzene, hence no back supply of electron from the ring, and that is happening because the loss of planarity has happened. Now COH p orbital are not in the same plane with benzene carbons p orbitals, and hence no resonance is taking place. So this oxygen is still carrying the positive charge, and hence it will kick out the hydrogen much more faster. Let's understand, is it only ortho effect which is affecting the substituted benzoic acid acidic strength, or there is something else, or ortho effect is just due to the steric inhibition of resonance, or there are other effects also participating in it? So one is ortho effect is due to the SIR. Now there are other factors also which contribute in causing the ortho effect. Let's understand those also. Now here I have taken an example. What example I have taken? That COH is along with OH over here, and OCH3 is here. So if you remember, I told you in SIR that OH neither contributes in SIR, basically neither it faces SIR nor it contributes in SIR. So if OH is present along with COH, what do we expect is it's not going to impact the COH acidic strength. Basically it is not going to increase the acidic strength of COH. Instead, COH is an electron donating group over here, and hence its acidic strength would be relatively lesser. Otherwise all ortho substituted compounds have better acidic strength, but here the acidic strength is lesser due to its electron releasing group. Okay, due to its electron releasing group and no SIR. If I talk about OCH3 group over here, I have told you it doesn't show ortho effects. Let's not consider that point. Let's not speak about the exception over here. If I talk about steric inhibition of resonance, which I have explained to you, in SIR, OCH3 is not exception. OCH3 will produce that repulsion, and COH will go out of the plane, and hence this acidic strength of COH should be higher, right? OH will not show SIR, so acidic strength should be less. OCH3 will show SIR, its acidic strength should be higher. So ideally, according to the acidic strength, your second should be more acidic than first, but this is wrong. Okay, what is the right answer? Right answer is first is more acidic than second. That means it is not only SIR which is participating and which is causing ortho effect to happen. There is definitely something else which is also contributing in the ortho effect. According to SIR, if SIR was the only criteria, then OH doesn't participate in the SIR, but OCH3 is. So OH wouldn't make your COH out of the plane, and hence its acidic strength would be lesser due to its electron releasing effect, whereas OCH3 does participate in SIR and hence will make your COH out of the plane, and the acidic strength of this molecule will increase automatically. Right? So in that way, your acidic strength for second should be more than first, but actual order is first is more acidic than second. There is definitely something which we have missed out here. There is definitely some more impacts or more effects which we have not spoken about, due to which it is following the ortho effect, and your OH is making it more acidic than OCH3 even without SIR. So what are those? So ortho effect due to electronic factors. There are some other electronic factors which also contribute in ortho effect and which causes the ortho effect. What are electronic effects? We have spoken about inductive effect, we have spoken about the resonance effect, mesomeric effect, and so on and so. There are some other things also which is called as hydrogen bonding, which you would have learned in the physical chemistry. Hydrogen bonding or electrostatic force of attraction, even these are the electronic effects. So electrostatic force of attraction, hydrogen bonding, these are very, very important factors, along with hyperconjugation, inductive effect, and resonance, which affects the acidic strength or ortho effect of the molecule. Okay, so let's understand. Let's take an example. I'll explain you. Your benzoic acid with OH is more acidic than OCH3. If you talk about this OH, though OH is not giving you any SIR, okay, and it is electron releasing, then the idea is that the acidity should be lesser. But what exactly happens? Let's see what happens in its conjugate base. Once the benzoic acid kicks out its hydrogen, once the ortho substituted ortho hydroxy benzoic acid kicks out its hydrogen, this is what you will get as a conjugate base. And this conjugate base is highly stable. This is stable because of what? This oxygen is carrying a negative charge, and this negative charge is this oxygen is carrying a negative charge, and this oxygen carrying negative charge is forming hydrogen bond with the OH's hydrogen. OH hydrogen is making hydrogen bond with the oxygen carrying negative charge, and it is coming into this and this is forming a cyclic kind of structure. Just look at it. There is a CO, and then I have shown you a dashed bond line here. This dashed bond line is nothing else but a hydrogen bonding. Okay, and then this is a hydrogen over here and this is oxygen. Mind it, hydrogen bonding is not an actual overlap. This is just a force of attraction, or you can say hydrogen bonding doesn't follow the hybridization. It doesn't happen through the hybridized orbitals and so on. This is a different type of attraction which happens between fluorine, nitrogen, oxygen with hydrogen. So fluorine with hydrogen, nitrogen with hydrogen, and oxygen with hydrogen generally do this hydrogen bonding, and this makes your molecule highly stable. Not only this, the hydrogen bonding is happening. Along with that, after the hydrogen bonding, it is forming a 6-membered cyclic ring. What all 6 members are there? First is this carbon, second is this carbon, third is this carbon, fourth is this oxygen, fifth is this hydrogen, and sixth is this oxygen. So it is 6-membered cyclic ring. Whenever, due to hydrogen bonding, if 6-membered cyclic ring forms, it is an extremely stable state. Very, very stable state. Okay, so this is a fact. You should know this, that after the hydrogen bonding or due to the hydrogen bonding, if 6-membered cyclic ring forms, it is actually a very stable state. And we have understood this. Stable, the conjugate base is better acid your molecule is gonna be, because it is going towards more stability. It'll definitely would like to kick out its hydrogen so that it can attain that stable state. So its conjugate base is extremely stable, and that is why it is much more acidic than your benzoic acid with OCH3, even though your OH does not participate in steric inhibition of resonance. So your ortho effect is not just because of SIR, but also because of the electronic factor. Which electronic factor worked over here? Hydrogen bonding. That too, after hydrogen bonding, we are getting a 6-membered cyclic ring, which is making my conjugate base much more stable. And that is why your ortho hydroxy benzoic acid is much more acidic than your ortho methoxy benzoic acid. Exactly same way, look at this molecule. I have COH with OH and OH over here. 2 OH are on the ortho positions. Both will not participate in the SIR. But what will happen? It will be further more acidic than your benzoic acid with OH at one position. How it is much more acidic? When the benzoic acid will lose its hydrogen, it will become O, and then there will be a resonance among these oxygens. So there will be a partial negative and partial negative charge over here. Here is your OH and here is your OH. So this hydrogen will form hydrogen bonding with this oxygen, as well as it will form a hydrogen bonding with this oxygen. So basically 2 6-membered cyclic chains due to the hydrogen bonding on both the sides further makes this molecule extremely stable, and that is why your di-ortho substituted benzoic acid is much more acidic than single or mono substituted benzoic acid. and then it is still more stable than your normal benzoic acid. Okay, and what is substitution over here? You can write di-ortho-hydroxybenzoic acid or mono-ortho hydroxybenzoic acid. Both of these are highly acidic. Out of it, di is furthermore acidic. Okay, and then if you compare them with the OH on the meta position or on the para position, how will you compare it? If the OH is on the meta position, then OH cannot show the resonance effect. So it will be only showing its inductive effect, which is electron withdrawing. So this is minus I. Okay, and if at para position, if this OH is present, then it can show electron withdrawing effect. So how will be the order if you want to, if just in case you want to arrange it in the order, how will be the order? Here di-ortho-hydroxybenzoic acid will be the most acidic one due to ortho effect, not due to SIR. My bad, I have written SIR here. Not due to the SIR, but due to its electronic effect, that is hydrogen bonding. Then relatively lesser acidic is your ortho-monohydroxybenzoic acid, and again the reason is ortho effect, but again this is due to hydrogen bonding. Ortho effect is due to the hydrogen bonding. What is ortho effect? Ortho effect means any group is present on the ortho position will increase the acidic strength of your benzoic acid. Then your meta is more acidic. Why your meta is more acidic? Because it is electron withdrawing effect on the meta position which is working. OH in resonance is electron donating. OH in inductive effect is electron withdrawing. I told you on meta position, resonance doesn't work. It is only inductive effect which works. So it is electron withdrawing effect. So it is electron withdrawing group, hence will increase the acidic strength. And if OH is on para, it is showing its effect as electron donating. So it will decrease the acidic strength, and hence it is the least acidic over here. Most acidic, di-substituted, then mono-substituted at ortho position, then your meta, and then your para. I hope you have understood, and that's how you have to analyze your benzoic acid questions, and that's how you have to solve them and arrange them in their acidic strength order. Now, let's quickly see a few more examples. I have benzoic acid with NO2. First of all, this NO2 will cause SIR. Even after causing SIR, the COH will kick out its hydrogen. Once it will kick out hydrogen, it will form this kind of group COO minus on both the sides. Oxygen carrying negative charge will also have electrostatic force of attraction with nitrogen with a positive charge, and hence that force of attraction plus SIR will totally overall cause the ortho effect and will make this molecule highly acidic. Now, if I have to arrange these groups, COH with NO2 on ortho position, on meta position, and on para position, how will I arrange? And then there is benzoic acid also. This has to be most acidic. Why? Because first of all, this NO2 is electron withdrawing through resonance also. It is electron withdrawing through inductive also, and it is causing the ortho effect also. So overall, all the three effects in general makes it extremely acidic. Then comes your NO2. In NO2, it is only minus I which is working. So it is electron withdrawing, but not as much electron withdrawing as the resonance would have made it. So hence it should be lesser acidic ideally. Look at the para position. Para has minus M and minus I. So it is causing more acidity to COH than your meta. So first, most acidic should be the first compound, then should be the third compound, then should be the second compound, and then should be your benzoic acid. Benzoic acid may normally there is no effect working, no electron withdrawing group present. Electron withdrawing group due to inductive effect on the meta position will be least acidic. This NO2 on ortho will be most acidic due to ortho effect, inductive effect, mesomeric. Every effect is working here, and every single effect is basically contributing towards the acidic strength. Look at the next few compounds. Now I have to arrange this COH with CH3 on ortho, meta, para, and then benzoic acid. I have to arrange them in the acidic strength order. Let's understand how we have to do it. What all effects CH3 can exhibit? It can exhibit plus I effect due to the inductive plus hyperconjugation. So basically donating through inductive, donating through hyperconjugation, and it also exhibits ortho effect. CH3 on meta position exhibits only plus I, that is inductive effect, donating inductive effect, and on CH3 on the para position does show hyperconjugation and inductive. Both are electron donating. So this is electron donating, this is electron donating, and COH doesn't have any electron donating effect. So first of all, we have to understand that even though it is plus I and plus hyperconjugation, this will have least impact. I mean, hyperconjugation will not work over here because it requires resonance, and plus I does show its impact, but ortho effect is basically making this COH out of the plane and hence making this OH much more acidic. O will carry a positive charge and there will be no back supply of electrons. That's why this O will be desperate to kick out hydrogen and it will be more acidic. Okay, so this is gonna be more acidic irrespective of plus I and plus hyperconjugation. Then come to benzoic acid. It doesn't have anything which can decrease the acidic strength. Electron donating impacts decrease the acidic strength. So first of all, your ortho substituted benzoic acid will be most acidic. Then comes your normal benzoic acid. Now look at the meta substituted benzoic acid. Here only inductive effect is working, which is electron donating. Here in case of para, hyperconjugation and inductive both are working and both are electron donating. Hence this should be more acidic than this one. So then comes second and then comes your third. Okay, so understand this very carefully. You should write the effects of each and every group present along with the benzene and COOH, so that you can understand their application. You can understand what all different effects are working and how will they play their part and how will they increase or decrease the acidic strength. Similarly, let's quickly look at these questions also. I have fluorine here, chlorine here, bromine here, iodine here. In all the cases, SIR will be working, right? So we can't say that SIR is not working, but bigger the atom is, better will be the SIR impact. So even though all the four groups are participating in the SIR and making COH more acidic, but bigger the atom is, better will be the SIR. Hence most acidic will be or this group, then this, and then this, because iodine is the most bigger element among all these. Okay, now come to the next. We have discussed similar thing earlier. I have now benzoic acid with NO2, benzoic acid with OCOCH3, benzoic acid with COCH3, benzoic acid with NHCOCH3, and now we have to understand how it will affect the acidic strength. NO2 present over here will have minus M and minus I, both are electron withdrawing effects. All of these groups are showing SIR. All of these groups are showing you ortho effect. Okay. Now here you have OCOCH3 here. Through resonance, it is electron donating, whereas through inductive effect, it is electron withdrawing. So overall impact of electron withdrawing effect is relatively lesser. Okay, it will not be able to withdraw much more strongly because it will be donating most of the time. So those two effects will clash with each other. Here this OCOCH3 is again electron withdrawing through resonance also and electron withdrawing through inductive also. And here for NH, again it is more electron donating than withdrawing. Its inductive effect is withdrawing and its resonance effect is donating. So here if you talk about the order, more the minus M and minus I is more the electron withdrawing factor is involved with the functional group, more stronger will be the acidic strength. Lesser the electron withdrawing part is, lesser stronger that group will be, and hence lesser will be the electron withdrawal from the whole group or from whole benzoic acid, and it will decrease the acidic strength. So most acidic will be among this group from COCH3 and NO2. NO2 is better electron withdrawing group in terms of inductive effect also. Okay, because nitrogen is better electronegative element, hence this will show better electron withdrawal and will make this COH more acidic, as well as it will have that electrostatic force of attraction also, which will make its conjugate base much more stable, hence this is most acidic. So basically acidic strength order will be in such a way that electron withdrawing effect wherever it is more will make the benzoic acid more acidic, and lesser the electron withdrawal effect is due to resonance or due to inductive or whatsoever, lesser will be the acidic strength. So it should be either first one or the third one which should be most acidic. So first one is most acidic because NO2 is more electronegative than your COCH3. So first, then comes third. Now there is a comparison between second and fourth. In case of second and fourth, oxygen is definitely more electron withdrawing through the inductive effect as compared to nitrogen, right? And hence this will cause more acidity as compared to this. When we talk about the second compound and the fourth compound, both are electron donating through resonance but electron withdrawing through inductive. Now when you talk about donating effect is definitely overpowering your inductive effect, but as we have already discussed that COH is out of resonance and its mesomeric effect should not affect your COH acidic strength much. Hence inductive effect is something which will be important to check over here. Oxygen is more electronegative than nitrogen over here, and hence will show better electron withdrawing inductive effect, and hence this will be more acidic as compared to this one, because nitrogen is lesser electronegative as compared to oxygen, and hence will be able to withdraw electrons through inductive effect relatively lesser than your oxygen. When SIR is there everywhere, or when ortho effect is there everywhere, then what do? Then you compare their mesomeric and inductive effect both. If mesomeric and inductive both are electron withdrawing, then they definitely increase the acidic strength drastically. If mesomeric effect and inductive effect are contradicting to each other, then you take the inductive effect into more priority, and then you talk about it, and then you check the inductive effect, which one is showing the better electron withdrawing inductive effect, that will be better in the acidic strength. That's how you have to check. Okay, so first is most acidic, then third, then second, and then fourth. When this is something which I have mentioned. If SIR is present in all, then electronic effect will work. We will not talk about the SIR. Look at the next compound now. Next compound, what we have NO2, CH3, COH, and SO3H on the para position. So no SIR here, no ortho effect over here. We are talking about the generic mesomeric effect and the inductive effect. NO2 tends to show -M -I. So this is strong electron withdrawing. This is CH3 is electron donating through inductive and hyperconjugation. Strong electron releasing. COH with COH, again strong electron withdrawing. And SO3H, when you compare COH and SO3H, both are acidic groups, by the way, and better acidic group is your SO3H. So here, when you say which one is better acid, we are not talking about COH over here. COH is weaker acid than SO3H. Sulfonic acid is better acidic. So basically, what impact the COH shows on SO3H part, that is important, not the other way around. If the chances here that COH can lose H plus and SO3H can lose H plus, SO3H will lose hydrogen faster, and hence we are checking the acidic strength of this group. So basically impact of COH will be on SO3H acidic strength, or you can say sulfonic acid will get affected by COH, not COH will get affected by SO3H. Okay, so here when we are checking the acidic strength, we are basically checking the acidic strength of SO3H, not COH. Let's see their effects. So your NO2 shows -M -I, this is plus H plus I plus H, this is -M -H, and this COH is again -M -I. Now in the fourth compound, if you see, they have anyways a very strongly acidic group, that is sulfonic acid group, and it has a COH present here, which is both the ways electron withdrawing through inductive effect also and through mesomeric effect also. That is why this is going to be the strongest acid. SO3H is anyway stronger acid. Now compare between the so this is automatically the most acidic group or acidic compound, fourth one. Now the comparison comes between the third one and the first one. Okay, because both have the electron withdrawing groups present in it. Which one is better electron withdrawing? When you compare COH and NO2 is better electron withdrawing. Why? Because nitrogen is better electronegative. It will be able to withdraw electron density much more strongly through the inductive effect. Mesomeric effect is same for both, but through inductive effect, NO2 is more electron withdrawing. Hence, overall electron withdrawing capability of NO2 is more than COH. So first one will be more acidic than the third one. So first come next, then third, and then second. Second is last because it has electron releasing groups rather than electron donating groups. So electron donating group increases the acidic strength, electron releasing group decreases the acidic strength. Again, I'll explain you why fourth one is most acidic over here. Fourth one is most acidic over here because it has a very acidic group present, that is SO3H. It is highly acidic, is much more acidic than COH. It has good electron withdrawing group present over here, that is COOH. So presence of a very good electron withdrawing group with a very, very strong acidic group, that is SO3H, makes this molecule highly acidic. We cannot say that NO2 wala thing should be more acidic. Why it is not, when NO2 is a better electron withdrawing group? It is better electron withdrawing group, but look at the group also, which is showing acidic strength. When we compare COH and SO3H is anyways capable of releasing hydrogen much more faster than the COH. So even little lesser electron withdrawing group will also increase its acidic strength drastically. Okay, so that is why this is most acidic, then first, then third, and then second. So here we are done with a lot of questions of acidic strength. In next class, we'll talk about more questions on acidic strength, and then we will start the basic strength order. how basic strengths get affected by different other factors, what is the general basic strength order, what is PKB, how to figure it out, what increases the basic strength, what decreases the basic strength, all that we will discuss in the next class, and few questions of the aesthetic strength. Okay, till then, go through this video, try to understand it, and ask me if you have any doubts in the doubts class.